Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosin, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question answer window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the question and answer window. Your questions in the window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, William Rushton Jr. from Bio-Rad Laboratories.
Thank you, Leah. Today I'm going to be talking about exploring on-column mAb aggregate formation and self-generated on-column pH gradients with cation exchange resins. Here you see a brief overview of the two Bio-Rad cation exchange resins that I'll be discussing today, Unisphere S and Nuvia HRS. Both of these offer some unique selectivities that could be helpful for your purification challenges. I'm going to move into speaking about some special considerations for cation exchange aggregate removal. There have been a number of studies that show a two-peak behavior during mAb elution from cation exchange resins. This can be due either to conformational changes in the protein during the binding step or to reversible self-association of the mAbs at high salt and protein concentrations during the elution. Both the conformational changes and mAb self-association lead to on-column aggregates. However, the degree of on-column aggregate formation may be resin and mAb specific. So here you see this two-peak behavior described on Capto SP Impress. The feed contained 10% aggregates. It was loaded onto the column, and during elution with that salt gradient, the first peak showed monomer, and then the second peak showed monomer and then aggregate. Upon re-injecting some of the first peak onto the column, they got a similar peak splitting, which is suggesting a reversible association on this cation exchange column. As a consequence, there's a lower yield of pure monomer. As they began to look at some of the possible clauses, including elution salt concentration, elution pH, and elution residence time, they began to ask, could the cation exchange resin type itself lead to any role into this self-association? So here you see 4 chromatograms of 4 different resins, and 3 of the 4 are showing a complete second peak, and the fractogel is showing a significant tail, but does lead to the suggestion that the cation exchanges themselves could be assisting with this self-association. This work was then continued by another collaborator, and in this case they decided to evaluate 6 different resins. They did 2 parts of the study. The first part, as exhibited by the dashed lines, they loaded the column, washed and eluted immediately after loading. And then for the solid line, they loaded the column, held for 1,000 minutes on column, and then completed the elution. And what you see is, for all cases, there's the beginnings of a second peak, with the exception of Nuvia HRS. The fractogel showed the highest amount of this self-association, and as I mentioned previously, the Nuvia HRS did not appear to show any self-association. The work then continued by studying the effect of the loading buffer on mAb aggregation. With cation exchanges, our standard practices run at low pH, low conductivity, and a slower flow rate to try and maximize that binding capacity. However, the observation by these chromatograms on the left show that low pH, low conductivity, and the long loading time seem to lead to that two-peak elution, with the exception of the Nuvia HRS. One final example is the 3-peak elution induced by the porous XS resin. So here you see 6 different times across the 1,000-minute hold, and at 0 minutes you see all monomer in that 2-peak based on the hydrodynamic radius. But as time goes on to 10 minutes, you see an increase in that second peak, but the hydrodynamic radius is still monomer. By 30 minutes, you're starting to see a third peak form and the hydrodynamic radius of that third peak increase. By 60 minutes, it's become more pronounced, and again, you can tell by the hydrodynamic radius that aggregate is forming. And by the end of the 1,000 minutes, the two peaks that are left are primarily aggregate with a little of that second peak that you saw at the 0 minutes still remaining. Finally, here's a comparison of Nuvia HRS with the porous excess. Nuvia HRS has a homogeneous surface, and as you can see by the chromatogram, has a single peak in the hydrodynamic radius showing monomer, whereas the porous excess, with its weak binding sites and strong binding sites, can lead to a surface-induced mAb conformational change and the aggregation as shown by that third peak and the increasing hydrodynamic radius. Of all the resins tested under the mentioned conditions, Nuvia HRS shows minimal formation of on-column aggregates. We know this behavior is not due to its particle size because porous excess, which has the same particle size as Nuvia HRS, demonstrated a different elution behavior and aggregate formation. These results underscore the importance of screening multiple resins during mAb purification process development, especially for aggregation-prone mAbs, not only to minimize the potential of on-column aggregate formation, but also to optimize recovery. Without this screening, it is difficult to predict the interaction and elution behavior of different mAbs on any given resin. I'd like to transition now to talking about self-generating on-column resin pH gradients. Now I'm going to talk a little bit about the mechanism of self-induced pH gradient formation. Unosphere S with its acrylamido backbone has a high level of carboxyl groups within the resin. What this means is that at a given pH, these carboxyl groups are in equilibrium with the sodium and protons from the mobile phase. However, following a step change in salt concentration or buffer pH, the equilibrium shifts and the carboxyl groups reversibly gain or lose protons, resulting in a local pH change. This then starts the initiation of a pH gradient which continues to form until both ionic and/or pH equilibria are reestablished. Due to the presence of the large number of carboxyl groups on Unosphere S, the gradient lasts for a relatively large number of column volumes. This provides a significant window for protein deabsorption, thereby enhancing the resolution. A study was done to compare the pH gradients on different cation exchange resins. So here you see three different cation exchange resins were tested: Unosphere S, Nuvia HRS, and SP Cephalose Fast Flow. The things to note mostly in this table are the weak acid group content. For Unosphere S, it's 170, Nuvia HRS is 25, and SP Cephalose is 5, leading to a total acid group content for Unosphere S of 310, 170 for Nuvia HRS, and 200 for SP Cephalose Fast Flow. In order to determine the extent to which other cation exchange resins show similar on-column pH gradient formation, pH transition during salt steps were compared for Uno S, Nuvia HRS, and SP Cephalose Fast Flow. pH transitions were studied in response to a 0 to 0.5 molar sodium chloride step gradient and 0.02 normal sodium acetate buffer, followed by a decrease to 0 salt in the same buffer. With all three resins, the pH decreased with increased salt concentration. The opposite effect on the pH was observed with a decrease in salt concentration. All resins showed a pH drop of 1.4 units from 5.5 to 4.1 immediately after the introduction of salt. However, the duration within which the pH returned to operating pH of 5.5 varied significantly. The duration of the pH drop for the Unosphere S was 7.5 CVs, in contrast to 0.8 CVs for Nuvia HRS and only 0.2 CVs for SP Cephalose Fast Flow. This difference between the duration of the pH gradients is, at least in part, dependent on the weak acid group content of the three resins. Unosphere S has the most carboxyl groups in its backbone. These carboxyl groups can contribute a high number of protons into the solution over a longer period of time, thereby increasing the duration of the pH gradient. In contrast, both Nuvia HRS and SP Cephalose Fast Flow have lower weak acid group content. Unosphere S took 35 CVs to return to the operating pH of 5.5 after the decrease in salt concentration, which is considerably longer than the 9 CVs for the Nuvia HRS and 6.5 CVs for the SP Cephros Fast Flow. These results indicate that although most S-type resins have residual carboxyl groups and demonstrate the pH gradient effect to a certain extent, only Unosphere S has sufficient carboxyl groups to allow the formation of gradients with usable durations. Next, I'm showing a comparison of protein resolution between Unosphere S, Nuvia HRS, and SP Cephros Fast Flow. A mixture of alpha-chemotrypsinogen and lysozyme in 20 millimolar acetate buffer was applied to the columns. A salt gradient of 0 to 750 millimolar salt at pH 5 was introduced for protein separation. As you can see by the chromatograms, both proteins were resolved by all 3 resins. However, Unosphere S, due to its efficient pH gradient induction, provided the best resolution between the peaks. The peaks were 10 CVs apart for Unosphere S, 7 CVs for Nuvia HRS, and 4 CVs for SP Cephros Fast Flow. Next, I'm going to describe some examples of protein separation on the self-induced pH gradient of Unosphere S. The ability of Unosphere S to resolve proteins with small differences in pI was evaluated through elution of ovalbumin, BSA, and transferrin. This was performed with a pH 4.5 to 7 steps using buffers containing a 10-to-1 ratio of acetate and phosphate mixtures with 0.04 molar salt at different mobile flow rates. The conductivity remained very low throughout the separation, between 2 and 3 millisiemens. Both conductivity and pH traces demonstrated little sensitivity to the flow rate. The 3 acidic proteins were well separated despite their close pIs and eluted an order of their pI during the pH gradient. Ovalbumin and BSA, which differ by a pI of 0.1 units, were separated by about 5 CVs. Next, I'm going to talk about the separation of native superoxide dismutase from its pegylated form. STS page analysis shows that native SOD appears as a single prominent band, whereas PEG SOD is more heterogeneous with a smear of higher molecular weight bands. Chromatography of SOD on Unosphere S resulted in 2 major peaks, which presumably correspond to 2 charged isoforms of the native protein, since only 1 band was visible by STS page analysis. PEG SOD eluded as 1 major peak and was confirmed to be that of PEG SOD. To demonstrate the effectiveness of the on-column pH-induced method, a 1-to-1 mixture of native SOD and PEG SOD was applied to the column. As shown in the figure, a pH-induced gradient resolved the mixture into 3 distinct peaks, each corresponding to their respective positions as identified by chromatography of SOD and PEG SOD separately. These results demonstrate partial resolution of the native and pegylated protein using self-induced pH gradient chromatography with Unosphere S. Further resolution may be possible with an even shallower pH gradient. Alternatively, additional purification of the low-salt eluate can be accomplished with an orthogonal chromatography step. Finally, I'm just going to offer a little advice on selecting cation exchange resins. So some things to consider. Your target binding capacity and selectivity to make sure that you have the right resin for your application. You want to have good resolution and recovery of your target, as shown by the earlier studies with HRS. If you're not able to get all your target off due to, say, on-column aggregation, this could be a challenge. This also rolls into impurity removal by having a resin that can selectively remove impurities that are undesirable. You can improve your yield. pH gradient formation. The Unosphere S showed superior self-generated pH gradient formation compared to other resins. This capability provides a better resolving power over traditional pH gradient techniques, and you can use that to exploit separation of proteins with very close pIs. Having good knowledge of your target stability can be very helpful. You don't want to be operating in conditions that might lead to loss of function of your product. And then finally, you really want to screen multiple resins as much as you can. It's always good to have a good library of options depending on what your challenge is so that you're able to get your product off as high purity and as high yield as possible. Finally, I'd like to thank you for your time and attention and just give a little information regarding Bio-Rad. We have the ability for method development. We have a worldwide network of experts that are able to assist you and come on site as needed. We have a dedicated technical support team to provide process assistance. We will support you throughout the life cycle of your process, including assistance with process transfer and regulatory procedures. Please check out our online resources at bio-rad.com/library. And if you have any questions regarding resin samples, want to speak to one of our scientists, view some of our packing tutorials, or even request a customized seminar, please feel free to email us at process@bio-rad.com. Again, thank you very much, and I'd be happy to take any questions that you might have.
Okay, thanks, Bill. So how do you know that Unosphere S can reproduce the gradients run after run?
Well, that's a great question, Leah. As people know, having that reproducibility is critical for when you're doing your protein separations so that you don't see changes to the pH that could impact your separation. So Bio-Rad actually did a study where we examined 3 different lots of our Unosphere S resin and compared the pH gradient, and we were able to demonstrate reproducible results so that when customers then get the resin, they can feel comfortable that they'll be able to accomplish the same.
Okay, so how does the particle size and structure impact the separation power for closely related charges?
Well, a smaller particle is going to give you better resolution. So if you look at, say, NUVIA HRS, it's a 50 micron bead, but the structure internally to that also plays a difference. So part of the talk was between NUVIA HRS and the porous excess. Both of them are 50 micron beads. However, they both behave differently when you look at the separation and the formation of aggregate. That's largely due to the structure of each of the 2 resins. So you have to look at both the particle size and the internal structure of the resin to find the proper separation that you're looking for.
Okay. Well, it looks like we're running out of time and we have time for just one more question. If we didn't get to your question, we will be passing those on directly and Bill can follow up with you. And go ahead and just keep typing in any questions. We'll be able to include those as well. But the last question for the webcast is, what makes the Unosphere S resin more effective in forming a self-generated pH gradient compared to other resins?
I think that has to do with the large number of carboxyl groups that are found on the acrylamido backbone of the Unosphere S resin. A lot of other resins have a very low weak acid content, and Unosphere S with that high level weak acid content actually enhances the formation of those on-column pH gradients.
Okay, thank you, Bill. And thank you to our audience for joining us. The recorded version of this webcast will be made available for on-demand viewing, and as a registered attendee, you'll receive a follow-up email notifying you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.